Alright, in this video I'm going to talk about the total derivatives. That is the second topic in chapter 8. So far we studied several things about the derivatives. So in case of a single variable function, so y is given by f of x, then we can examine the rate of change using the derivative. So dy over dx is f prime of x. So we studied how to compute the derivative using differentiation rules, or we can rewrite this in a differential form. So dy is f prime of x dx. So this form highlights the fact that derivative forms linear relationship between two differentials, dy and dx. Okay. So derivative is the rate of change because we divided dy by dx, and differential is more like a variation of function. Okay, so a linear approximation of function change. All right, and then in case of two variable functions, so now f depends on two variables x and y, and we define the partial derivative. So the partial derivative is the derivative. So that pertains to rate of change. So if we consider partial with respect to x, it tells us at which rate does z change for a tiny change in x. So we keep variable y constant, and we treat x as the only variable. And if x changes, at which rate the function f or variable z change. That is a partial with respect to x. Okay, so partial, this is a derivative. So that is the rate of change of function in response to tiny change in x. Okay, and keeping the other variable constant. And we also talked about a total differential. Differential is a total variation. So now how do we treat total variation of this function? Because now function depends on two variables, and because of the linearity defined by derivatives between two differentials, we can write total differential function f as the sum of two partial variations. Okay, so the differential is more like a variation. So how much do we expect variable z to change for a tiny change in both x and y? That is a differential. Okay. Now the remaining thing is, can you consider the rate of change in this function? The answer is yes. That is pretty easy. That's just a natural extension of a total differential. Okay, and this total derivative, so that is called the total derivative. Okay, the rate of change of function when both x and y change. Okay, so we can define, so when f depends on x and y, we can define df over dx. Okay, so the situation is like this. We have two variables. Okay, and then both will influence function f. Okay, now we change x only, but in fact there is a hidden channel between x and y. A change in x now induces change in y. So there is a hidden channel here. Okay, so if x changes a little bit, y also changes, and that in turn changes in that in turn influences function f. Okay, so in this case, we start with a change in x, but change in x also induces change in y, and that in turn influences function f. Then we can now consider at which rate function f change over tiny change in x. Okay, so that is the basic idea of a total derivative, and you may wonder, oh, this figure is slightly different from the previous because we didn't consider this kind of some hidden channel between x and y. So do we need another treatment for this? No, the answer is no. With this total differential, we can analyze a total derivative. So you can see in a very short second, total derivative is just the extension of total differential. All right. So the leading example is right here. So now we consider function y that is given by function f of x and w. And then x is so there is some association between x and w, so between these two variables. So one example is this, one economic example is this. So regard w as a pay or wage for employees, and x is a productivity. So pay for employee and their productivity will, influence the firm's profit. Okay? And suppose that owner of this firm increases pay, so increases wages slightly. Okay? Then it has a direct effect on, profit, because now the owner has to pay a little bit more, so it has a negative direct effect on profit. But there is another channel, by the way, because if pay increases, that enhances, employees to incentive to work hard. So that increases the employees' productivity. So we can anticipate the increase in X, and that has a positive, effect on the profit. All right. So, with this economic application in hand, now let's consider what is the total derivative of y with respect to w. Okay, once again, now w changes, but such a change in w also induces change in x, and that x also influences, value of y, so profit. All right, so this tree diagram shows that. So this tree diagram shows us, how does this function work? So how this function works, okay? And then anyhow, we wanna compute total derivative of y with respect to w. So at which rate profit increases or decreases, when we increase wage slightly, okay? So this is the derivative, so it indicates the rate of change of profit with respect to W. So in response to tiny change in pay. All right, then, because Y depends on two variables, we can first compute the total differential. So dy equals, a partial variation due to change in X, so change in productivity, and partial variation of profit due to change in pay. Okay, and then we just divide it by dw. Then we obtain dy over dw equals, so that is a derivative rate of change, right? And we have f sub x dx over dw plus f sub w. Now dw will be cancelled, so we have this one. Okay, then I can rewrite this because there's association between x and w. That is given by function g. And dx over dw, that is nothing but the derivative of this one. So I can rewrite this f sub x, now g prime of w plus fw. Okay, so that is the derivative firm, the total derivative firm of function f or variable y with respect to w. Okay. So the basic idea is how do we obtain this formula? Because now we consider change in w, right? So w changes really bad, as much as dw. Okay, and as I told you, change in w induces change in x, but this association is given by g, so x will change as much as, so dx is going to be g prime of w dw when w changes by dw, right? Because we have this relation, that means dx over dw is going to be g prime of w, and differential of x, so dx can be written as g prime of w dw, right? And with this, Now I can eliminate this one, this channel, because now I consider this effect by computing dx, by expressing dx as a function of dw. All right. Now we go back to the total differential one. So now dy affects y as much as f sub w dw. All right. And then change in x affects y as much as f sub x dx. Okay. So total differential is going to be sum of this. So total differential is this one, right? But dx is the same as, so dy is f sub x dx, but dx is the same as g prime of w dw and f sub w dw, right? And then dividing the both sides by dw, I obtain this form. Okay. Another way to see this, because we first consider this direct effect, this one is given by partial derivative, so we have f sub w. So once we consider this, so now I consider direct effect of change in w on change in y. So I consider this one. So after eliminating this one, after deleting this arrow, I will be left with this one. That is a composition, right? So the x is a function of w, and y is a function of x. Okay, so y is going to be a function of w. Y can be regarded as composite function of x and w. So now we have a channel. So the basic idea is, we originally function f depends on two variables x and w, but x is given by g of w. So why we can just start with a substitution. Just can make this function as a function of just one variable by way of substitution. So y is f of g of w and w. Okay, then that is a single variable function. So now we can define dy over dx, derivative, right? Normal derivative, and that normal derivative is going to be, because now we consider this w first. Then we have f sub x partial, and because by the chain rule, we first take the derivative of the outer function, but now we consider this w, so derivative partial with respect to x, and then we multiply by g prime, the derivative of the inner function, and then now we consider this one, the change in y due to change in this w, and that's going to be f sub w. Okay. So it does not matter, whether we start with a substitution, so making the original function be single variable function, and using the chain rule, we can obtain the total derivative like this. Or we can start by computing total differential, and then dividing by dw to obtain dy over dw, the desired total derivative, because the result is the same regardless. All right. So the difference between partial and total now is evident, very straightforward. So partial just considers, so partial with respect to w considers only this effect, right? But total variation, total derivative considers both direct effect and indirect effect. Okay. So total variation of y due to change in w, taking into account its direct effect on x. All right. So now let me do this one. Let me do this example to illustrate how to find the total derivative. Okay. So now y is a function of x and w. So let me first start with total differential. So dy is going to be 3 times dx minus 2w dw. Right? And then I divided by dw. dy over dw is 3 times dx over dw minus 2w. Okay, then there is some relationship between x and y, or x and w. So dx over dw, now derivative with respect to w gives me 3 times 4w plus 1 minus 2w. So total we have 10w plus 3. Okay, so that's a total derivative. Okay, so once you understand the total differential, how does function change over x and y? And we can start from that total differential, and just in order to find the total derivative with respect to w, then we can divide the total differential by dw to find the desired result. Okay. So draw a in this example, draw a tree diagram and find the total derivative dz over dy. So here z is given by function of x and y. Okay. And there is association between x and y. So x is given by function of y. Okay. So the situation is now we have y here. So there are three variables x, y, z. But change in y affects x. And the change in x will influence variable z, and y has a direct effect variable z. So y has a direct effect on variable z. Okay. So the way to disentangle this one. So how do you find dz over dy? So let me first find dz. Total differential for z is 8x minus 2y times dx, right? 4x squared becomes 8x, and 2xy, regarding y as a constant, then I obtain 2y, and 2y squared is a constant, so that goes away. And then partial with respect to y times dy. Now 4x squared goes away, negative 2xy's derivative, partial derivative with respect to y, becomes negative 2x, and then 2y squared becomes 4y, right? And then divided by, because we are looking for dz over dy. So let me divide it by dy. Right, to obtain this. And then dx over dy, because x is given by function of y, so dx over dy is, this is a y to the power negative 1, so negative y to the power negative 2. Okay, so I have minus 8x minus 2y y to the power negative 2 plus 4y. Okay, so this might be a one answer. So this might be a one expression of total derivative dz over dy. But when we find out dz over dy, that means we regard z as a function of y. Okay, so we may have to substitute. So we may have to rewrite this as a function of y. So x is given by 1 over y. So we substitute 1 over y to the power negative 2, and minus 2 over y plus 4y. Okay, because we want to see how does a variable z change over y, meaning that we consider z as a function of y. Okay, so this is not a partial derivative but total derivative, right? So we have to translate the expression into a function of y by way of a substitution like this. Okay, so now the previous idea can be extended to a function with several variables. So even though function has three independent variables, the idea is the same. We first compute the total differential dy and divide it by if we look for so in this case w of x, so change in w induces change in x1 and change in x2. Okay, sorry, originally function depends on two axes, x1 and x2, and additional variable w. Okay, so the underlying variable is a w, so change in w induces change in x1 and change in x2 via function g and h. Okay, and then change in hx also influences y, and that is given by function f, okay, through the function f. And then change in w also has a direct effect on y through the function f. Okay, so we have this kind of game tree, or we have this kind of tree diagram, all right? And then the way to find the total differential is the same as before. The only difference is because now we have an additional variable w, so total differential dy is going to be f sub 1, the partial with respect to variable x1, dx1, and f sub 2 dx2, partial with respect to x2 times dx2, and finally f sub w d sub dw. Okay, and then we can just divide it by w to obtain this one. Right? And then dx1 over dw is a g prime. So dy over dw is f sub 1 times g prime of w. Right? The derivative of x1 with respect to w. And dx2 over dw, this term, is going to be h prime. Okay? And finally, we have f sub w. Right? So, just as in the previous example, you can approach from, two different angles. So the first angle is, now think about changing w. So w changes by dw. Then the corresponding change in x1 is going to be g prime, dx1 is going to be g prime of w times dw1, or dw, because dx1 over dw is g prime, so dx1 can be written as g prime times dw. Right? And similarly, dx2, differential dx2 is going to be h prime dw. Okay, so now we considered these two channels. Okay, so after deleting these two channels, now we have three variables. Okay, so three variables independently change. Okay, so the total differential is going to be this one, so f sub x1 times dx1, but dx instead of dx1 we can substitute this quantity, so we obtain this one, and then the plus the partial variation from dx2, so f sub x2, so f sub 2 times dx2, but instead of dx2 we can substitute this one, h prime dw. And then finally, change in w also has a direct effect on y through this channel. That is a f sub w times dw. Okay, so the last one. Right, so after writing this total differential, we can divide it by dw to obtain the same expression. Okay, and the other angle is we first consider this direct effect. Now, y can be thought of as a composition between several variables, and then we can adopt the chain rule. to obtain the same result. Okay, let me skip that. All right, finally, let me do one more example. So draw a tree diagram. Let me, I just keep talking about game tree because this kind of diagram is also applied to game theory. And I've taught game theory for a long time. So, but yeah, draw a tree diagram and find the total derivative dz over dt given the function z. Now z is given by function of x and y. Okay. But x is also a function of t and y is also a function of t. So we have four variables here, z, x, y, and t. And t has a impact on x, also impact on y. So change in t brings about change in x or change in y. And x will influence z, y also influences. So change in y also influences variable z. Okay, so we have this tree diagram, right? And so this t, the underlying variable, has no direct impact on variable z. Okay, so in this situation, how do you find dz over dt? So dz total differential is f sub x, that is a 2x minus 8y times dx, and f sub y, 3y squared dy. Okay, and then we are looking for dz over dt, so we divide both sides by dt, then we obtain this one divided by dt. All right, so 2x minus 8y, dx over dt is the derivative of this one, so that's going to be 3. And dy over dt, derivative of this one with respect to t, so we have -1. Okay. So to arrange this expression, I obtain 3y squared minus 24y, okay? And I have a 6x from the first term, 2x times 3, and additionally negative 8x times -1, so 8x, so total 14x, okay? Because now we're looking for dz over dt, so we regard z as a function of t. So in order to write the final answer, we have to transform into function of t. So by substitution, so 3y squared becomes 1 minus t squared. Negative 24y becomes negative 24, 1 minus t. And 14x becomes 14 times 3t. Okay? So this one is going to be total derivative of function z. So this function with respect to t. Right? So the way to find the total derivative is very simple once we understand the total differential. Okay, so we first compute total differential, and if we want to look for dy over dx, then we can just differential by dx.